Something is coming out of Antarctica, and most people have absolutely no idea it is happening. Not slowly, not in some distant future. Right now, beneath the ice that covers a continent the size of the United States and Mexico combined, something is waking up, moving, and in some cases already breaking through to the surface. This is not a climate change debate. This is not a political argument. This is a story of what is physically happening to the coldest, driest, most remote place on Earth, what scientists have found buried under kilometers of ice, and why the next few decades will change the map of the world in ways that most people cannot even begin to imagine. Let us start with the numbers, because the numbers are staggering. Since 2012, Antarctica has been losing ice at an average rate of about 150 billion tons per year. That is not a typo. 150 billion tons every single year. To put that in perspective, if you stacked 150 billion tons of ice, you would cover the entire city of New York in a block of ice roughly 3 kilometers tall. And that number has been accelerating. Between 2012 and 2017, the rate doubled compared to the decade before. The data comes from a study published in the journal Nature in 2018, compiled by a team of 80 scientists across 44 institutions. This was not one research group with an agenda. This was the largest coordinated ice measurement study in human history. The place at the center of all of this is called the West Antarctic Ice Sheet. Scientists have been staring at it for decades with a mixture of professional fascination and barely concealed terror. The West Antarctic Ice Sheet holds enough water to raise global sea levels by roughly 3.5 meters. All of it. If it goes, Miami is gone, Bangkok is gone, large portions of Shanghai, Mumbai, and New York are gone. And the problem, the specific geological nightmare that makes scientists lose sleep, is something called marine ice sheet instability. The West Antarctic Ice Sheet rests not on bedrock above the ocean, but on bedrock that is actually below sea level, in some places more than 2 kilometers below sea level. When warm ocean water gets underneath the ice, it does not just melt from above, it melts from below, from underneath, in a process that is extremely difficult to stop once it starts. The ice effectively becomes unstable from the bottom, and when glaciers lose their footing from below, they do not retreat slowly. They can collapse. The specific glacier that scientists watch most closely is called Thwaites. If Antarctica is the sleeping giant, Thwaites is the giant's heart. Thwaites Glacier in West Antarctica is roughly the size of Florida. It is already responsible for about 4% of global sea level rise every single year. That might sound small, but 4% of global sea level rise from one glacier alone is an extraordinary number when you understand how many sources contribute to sea level rise globally. Thwaites has been called the Doomsday Glacier by researchers, not because scientists enjoy dramatic language, but because the data genuinely warrants it. If you want to subscribe to this channel and not miss what comes next in this story, do it right now. This is only getting more important. In 2021, the International Thwaites Glacier Collaboration, a joint American and British research effort involving over 100 scientists, published a series of findings that fundamentally changed the conversation. Their robot submarines, sent beneath the ice shelf and water temperatures that would kill an unprotected human in minutes, discovered something alarming. The warm water intrusion under the Thwaites ice shelf was far more advanced than previous satellite measurements had suggested. The water beneath the ice was not just warm, it was finding channels, pathways carved into the underside of the glacier and flowing through them in pulses. The melt was not uniform. It was targeted, surgical almost, eating away at the exact pressure points that hold the glacier in place. In January of 2022, researchers using satellite radar data published findings in the journal Nature Geoscience showing cracks spreading across the eastern ice shelf of Thwaites, in a pattern that one researcher, Aaron Pettit of Oregon State University, compared to a car windshield shattering. The cracks she was describing are not surface scratches. They are fractures running through ice that in some places is hundreds of meters thick. Her team estimated that the eastern ice shelf could collapse within 3 to 5 years from the time of that publication. That puts the window between 2025 and 2027. When an ice shelf collapses, it does not cause the sea level rise directly. The ice shelf is already floating, and floating ice displaces water, so its melting does not add to sea levels in the same way land ice does. What the ice shelf does is act as a cork in a bottle. It holds back the land-based glaciers behind it. When the cork is removed, the land ice behind it accelerates toward the sea dramatically. After the Larsen B ice shelf in Antarctica collapsed over 35 days in 2002, the glaciers behind it accelerated by up to 8 times their previous speed. 8 times. That is what happens when the break is removed. Now here is where the story gets even stranger. Because Antarctica is not just melting, it is also revealing things that have been locked under the ice for millions of years. In 2018, A team from the British Antarctic Survey discovered one of the largest volcanic regions on Earth, sitting underneath the West Antarctic ice sheet. 138 volcanoes, some of them potentially active. The discovery was made using ice-penetrating radar flown on aircraft across the continent, and the volcanic peaks they found range from 100 meters to nearly 4,000 meters tall, all buried beneath kilometers of ice. The question that immediately follows this discovery is obvious. If the ice thins, does the volcanic activity increase? The answer from geologists is not a simple yes or no, but it is deeply unsettling. There is a well-documented process called glacial isostatic rebound. When ice melts and the weight pressing down on the Earth's crust is removed, the crust rises. This is not theoretical. And you can see it happening right now in Scandinavia, where the land is still slowly rising from the weight of glaciers that melted over 10,000 years ago. In Antarctica, the ice is so heavy that it depresses the bedrock by hundreds of meters in some locations. As that ice melts and that weight is removed, the crust flexes. And flexing crust near volcanic systems can, under the right conditions, influence eruption frequency and intensity. Research published in the journal Geophysical Research Letters in 2017 modeled this process and found that under high melt scenarios, the frequency of volcanic eruptions in West Antarctica could increase substantially by around 2,100. But what is coming through the ice is not only geological, it is biological, and this part of the story may be the most surprising. In 2013, a team drilled through more than 800 meters of ice above a subglacial lake in Antarctica called Lake Whillans, a body of water that has been isolated from the surface for potentially millions of years. What they found was not a dead, sterile environment. They found life. Billions of microorganisms living in water that had been sealed off from the surface of the Earth, potentially since before modern humans existed. The research was published in the journal Nature and represented the first confirmed discovery of life in an Antarctic subglacial lake. Since then, surveys have identified over 400 subglacial lakes across Antarctica, many of them connected to each other through drainage channels. These lakes contain organisms adapted to conditions of total darkness, crushing pressure, near-zero temperatures, and complete isolation. Some of these microbes are metabolizing in ways that researchers do not fully understand. Some produce gases, some process iron, some break down organic material that may have accumulated over geological timescales. As the ice above them thins, and as meltwater changes the dynamics of these buried lake systems, some of these organisms are being flushed toward the ocean. In 2020, research teams tracking subglacial water flows confirmed that material from beneath the ice is actively draining into the Southern Ocean through conduits carved by meltwater. What is in that material, and what effect it will have on ocean chemistry and biology, is a question that science is only beginning to ask. Above the ice, the story of change is equally dramatic. The year 2023 broke records that scientists describe as genuinely shocking. Antarctic sea ice, which normally expands dramatically in winter to cover roughly 18 million square kilometers, reached its lowest maximum extent ever recorded since satellites began tracking it in the late 1970s. In September of 2023, the ice reached a winter maximum of just 16.96 million square kilometers. That was 1 million square kilometers below the previous record low. To put that in physical terms, 1 million square kilometers is roughly the size of Egypt. An entire Egypt-sized area of ice that should have been there was simply absent. If you are still watching this, you already understand this is bigger than most news coverage suggests. Share this video because this information needs to reach more people. The consequences of reduced sea ice are not limited to polar bears and penguins. Sea ice plays a fundamental role in regulating global ocean circulation. The Southern Ocean around Antarctica is one of the primary locations where dense, cold, salty water sinks to the deep ocean floor, driving the global conveyor belt of ocean circulation known as thermohaline circulation. This circulation system moves heat, oxygen, and nutrients around the entire planet. In 2023, a study published in the journal Nature Climate Change, authored by a team led by Matthew England at the University of New South Wales, used ocean models to project the future of Antarctic bottom water formation. The findings indicated that under current emissions trajectories, the overturning circulation in the Antarctic could slow by more than 40% by 2100. A slowdown of that magnitude would have cascading effects on global climate, ocean oxygen levels, and the food chains that depend on nutrient-rich deep water upwelling. The human geography of what melting Antarctica means is where the story becomes most immediate and most personal for billions of people. A sea level rise of even half a meter, which is within the range of projections for 2,100 under moderate scenarios, would affect hundreds of millions of people living in low-lying coastal areas. A rise of 1 meter would be catastrophic for dozens of major cities. A rise of 2 meters or more, which becomes possible if West Antarctic ice sheet instability accelerates beyond current models, would redraw coastlines on every continent. Bangladesh would lose roughly 17% of its land area. The Maldives, which sit at an average elevation of just 1.2 meters above sea level, would be largely submerged. The Netherlands, which has spent centuries engineering against the sea, would face challenges that could exceed the capacity of even its extraordinary flood management systems. In the United States, a 2-meter rise would flood large portions of South Florida, the Louisiana coast, the Chesapeake Bay region, and low-lying areas of New York and New Jersey. The cost of adapting to even moderate sea level rise in the United States alone is projected in the hundreds of billions of dollars. The city of Jakarta, Indonesia, home to over 30 million people in its greater metropolitan area, was already sinking due to groundwater extraction before sea level rise was factored into its future. The Indonesian government made the decision to move its capital to a new city called Nusantara in the island of Borneo, a project formally announced in 2022 with an estimated cost of $34 billion. Jakarta is not the only city making calculations like this. Many coastal cities around the world are now quietly investing in infrastructure that only makes sense if you believe sea level rise projections are real and accelerating. What makes Antarctica's story particularly difficult to communicate is the sheer scale and the distance. Most people will never go there. Most people will never feel the cold of the Amundsen Sea or stand on the surface of the West Antarctic ice sheet. But the effects of what is happening there will be felt by everyone alive today and by generations not yet born. The physics does not care about distance or borders. When Thwaites loses its ice shelf and the land ice behind it begins accelerating into the ocean, the sea level rise produced will be distributed across every ocean on Earth within roughly 40 to 60 years. Scientists at the Potsdam Institute for Climate Impact Research in Germany published modeling in 2023 suggesting that certain tipping points in the Antarctic system may already be locked in regardless of future emissions reductions. Once marine ice sheet instability in specific glaciers like Thwaites reaches a certain stage, the retreat becomes self-sustaining. The warm ocean water creates a feedback loop. As the ice retreats, deeper bedrock is exposed, which allows warmer deep water to access more of the glacier's base, which causes more melting, which causes more retreat. The glacier essentially pulls itself apart from the inside. Robert DeCanto of the University of Massachusetts Amherst and David Pollard of Penn State published a landmark study in 2016 in the journal Nature, projecting that under high emissions scenarios, Antarctica alone could contribute over 1 meter of sea level rise by 2100. That study represented a significant upward revision from previous estimates and caused substantial debate in the scientific community, with subsequent research neither fully confirming nor fully refuting its most extreme projections. The uncertainty in the science is real, but it is important to understand what the uncertainty means. Scientists are not uncertain about whether Antarctic ice is melting. It is. The measurements are precise and verified by multiple independent methods, including satellite altimetry, gravity measurements from the GRACE satellite mission, and direct field observation. The uncertainty is about how fast the most extreme scenarios will unfold, not about whether they will unfold at all. The most optimistic, realistic projections still involve significant sea level rise. The difference between acting now and acting later is the difference between manageable adaptation and existential displacement of hundreds of millions of people. The drilling programs continue. The robot submarines go deeper. The satellites pass overhead, collecting measurements to fractions of a millimeter. In 2024, the Thwaites Offshore Research Project deployed autonomous underwater vehicles under the ice shelf for the longest sustained period ever attempted, gathering data about basal melt rates and ocean water temperatures that had never been directly measured before. The lead researchers described what they found as both expected and deeply concerning, a combination that, in scientific language, translates to something close to dread. In late 2023, a study released by the British Antarctic Survey found evidence that parts of the bedrock beneath the West Antarctic ice sheet were significantly smoother than previously modeled, meaning that when glaciers there begin to slide, they will encounter less friction than scientists had calculated. Less friction means faster movement. Faster movement means faster ice delivery to the ocean. Faster delivery to the ocean means faster sea level rise. Every refinement in the data seems to tighten the timeline rather than extend it. One thing buried under the ice for at least 34 million years may end up being the most significant geological discovery of the 21st century. In 2020, researchers using airborne radar surveys identified what they believe is a remnant of an ancient forest beneath the ice in the Transantarctic Mountains. Not fossil impressions. Actual preserved organic material, roots and soil layers from a temperate rainforest that existed in Antarctica when the continent was still warm enough to support trees. This ancient ecosystem was frozen in place when Antarctica crossed a climate threshold and became the ice-covered continent it is today. As drilling technologies improve and as some surface ice retreats, these buried layers become more accessible. What they tell scientists about how quickly climate transitions happen in geological history is both scientifically invaluable and quietly terrifying. Antarctica is 34 million years old as an ice sheet. It took a long time to build, and it will take a long time to fully melt. But the relevant question is not whether it will all melt in one lifetime. The relevant question is whether the processes now underway have passed the point where human choices can reverse them, or whether we are now simply negotiating the speed of something that has already been decided by physics. The researchers who spend their careers on this question do not talk like people who think the answer is reassuring. Thwaites Glacier is currently retreating at roughly 14 kilometers since the 1990s. The data from underneath it shows warm water intrusion extending further every year. The eastern ice shelf is fracturing. The models that predicted stability have been consistently outperformed by reality in the wrong direction. The last thing most people expect to find under a continent covered in ice is a forest, a volcano fields, 400 hidden lakes teeming with ancient life, and a geological process capable of reshaping every coastline on Earth. But that is what is down there, and whether anyone is watching or not, it is moving. The ice does not negotiate.